Welcome to Pomodoro Joe for Friday, October 6th, 2023. Today we're looking at LeetCode problem 343, integer break. This is a medium problem. All right, we are given an integer n. We need to break it into a sum of k positive integers, where k is greater than or equal to 2. So we have to break our n into some number of positive integers more than 2, and maximize the product of those integers. Return the maximum product you can get. So, example 1, n is 2. Well, we can only split that into 1 and 1, so our answer is 1. So this can be 1 plus 1, 1 times 1 is equal to 1. All right, next, 10. Well, we can break 10 into a lot of different options. We could do 1 and 9, we could do 1 and 1 and 8, we can do 1 and 1 and 1 and 7, we can do 2 and 8, we can do, anyway, there's a ton of options. So our best answer here, it looks like it's going to be 3 and 3 and 4. So 3 and 3 is 6, 6 and 4 is 10, and then 3 times 3 times 4 is 36. Okay, and we also have a pretty short range here, from 2 to 58, so we could probably do an exhaustive search. All right, we'll put 25 minutes on the Pomodoro timer and we will get started. So I think I'll do this recursively. So let's start with a recursive function, def integer break recurse. And this will take some remaining number, so remaining n. All right, and now with our recursive functions, we always start with a base case. What is our base case? Let's see, if the remaining n, that's not it, that's equal to 1, we can't split it anymore, so we'll return 1. All right, do we have any other base cases? I guess if remaining n is 2, we can only split it one way, so we could also return 1. And in fact, this remaining n being 1 should almost never happen. It can only happen in the recursive case. It can't be the initial function, or it can't be the initial input. What else? Well, I guess we could also look at 3. If remaining n is 3, let's see, we can split that into 1, 1, and 1. It can be 1, 1, and 1. But that's just going to result in 1. 1 times 1 times 1. Or we could do a 1 times 2, and that's going to result in 2. And that's pretty much our only option. All right, so return 2. All right, then we get to 4. It's a little bit more complicated. It can be 4 1s. It can be 2 1s and a 2. It can be 2 2s. In fact, 2 2s are probably our best answer. That gives us 4. Otherwise, it's 1 and a 3. Okay, we're not going to do 4. We're going to move on. Let's do the recursive calls. So now that we've made it past our base cases, we can think of our recursive cases. So for our recursive cases, let's just go through and split this number, the remaining n, into 2 pieces. We'll have some initial piece, we'll call it I, and we'll have the remaining of the remaining n. So it's the remaining n minus I. So for every I in range, let's see, we don't want to start at 0. We want to have at least 1. So I'll go from 1 to remaining n. Now, this is not inclusive, so we won't go all the way to remaining n. We'll go to remaining n minus 1. So for I in range from 1 to remaining n, then our option will be to take this I and we will multiply it by the best option we can get back from our recursive call. So we're going to split our remaining n into I, let's say it's 2, and remaining n minus I, so remaining n minus 2. And we're going to do that for every possible I in range from 1 to remaining n. So this will be I times our recursive call on remaining n minus I. Okay, and now we take what's our best option. So let's have some result out here. Result, start at 0, and then let's see, our best option will be the result is equal to result if result is greater than option. Otherwise, we'll take this option. This is basically just saying the result is going to be the maximum of result, or our option. And then we'll return our result at the end. Cool. And then out here, we need to kick the whole thing off. So we'll return our function and we'll pass in n as the initial value. All right, so this is looking pretty good. Now, let's see. We have some base cases, then we have our recursive cases. One possible problem, I don't know if this is the right thing here, this result. It's possible that we pass in our value remaining n. That could actually be our return. We might not actually have to split this n into multiple pieces if we've already split it before. So this is tricky. If this is the first time we've called this function, we have to split this n at least one time. This is telling us we have to split it into some positive number of integers, some k number of integers. So we have to have at least 2 integers. If this is the first call into our recursive function, then we have to split it at least once. But if this is a later call to our recursive function, we don't actually have to split this number. It could be that our best option is just to return the number itself. So this could be remaining n. The only problem is we don't know if we've already gone through and split this or not. We could pass in some variable that's like, have we split it? We can have a Boolean, true or false. Let's try that to begin with. I think I have a better way to do it, but let's try that. So we'll have some thing here that's like first pass, and we'll set it equal to true on our initial call. And then all the other calls, we'll set it equal to false. All right, and now if this is the first pass, this actually won't work for us. This remaining n part won't work for us. So let's see, if this is the first pass, so remaining n if first pass equals false, or I can say if not first pass, maybe I'll do that. Otherwise, if this is the first pass, then the best we can do will be this remaining n minus 1. So we can have 1 times the remaining n. So this will be remaining n minus 1. And that's kind of weird. I think I have a better way to do this. It's a little bit weird, so let's see how this works, or if it works at all. Let's see, what did I do wrong? I'm missing my parentheses. Okay, so that seems to work. Let's see if it'll pass all the tests. We got a wrong answer, and it's a wrong answer on 4. All right, we didn't do very well. So clearly this isn't quite right. Let's see. If we have 1, we'll return 1. If we have 2, we can return 1. If we have 3, we'll return 2. Those all look okay to me. Let's see. These actually, now that I think about it, these can all live outside. These could be here. So let's do this. If we have 1, we return 1, but we should never have 1 in the beginning because it tells us here that we have to have at least 2, so we can get rid of that. All right, so if we have 2, we return 1. If we have 3, we return 2. Otherwise, we'll call our recursive function. First pass, the best we can do is remaining n minus 1. Okay, let's try this. Right, there is no remaining n out here. This is just n. Oh, my indentation's all wrong. Oh man, what a mess. Oh, I forgot to save my test case. All right, I think it was 4, so let's try 4. I'm just failing across the board today. All right, so 4 still doesn't work. We're returning 3, it should be 4. All right, so what's going on here? The best result is our 4. Let's see, first pass. Oh, in this case, our first pass is already covered by these, so I don't need this anymore because I've already done the first split. Okay, this is a mess now, but these basically, if I get past these, that means I've definitely made a first split. And that means this is no longer valid. This, if remaining n is 2, we could just return 2 at this point. Oh man, let's do this. I guess I still need my base case of 1. Okay, so that seems to work. Now that I've done that, let's actually add caching here, just to make it go a little bit faster. Okay, let's see how this does. All right, and now we pass. And let's see, we do really well actually. That surprises me. So we get an 80% for runtime and a 58% for memory, so that's pretty good. All right, we'll jump back here really quick. So this one has this tricky bit where the first time you go through this recursive function, you don't know whether or not you've split this at least one time. And according to the instructions, you have to at least split once, so you can't just use this value itself and return it. So the difficulty here is knowing whether or not you've split. So we've created this extra Boolean that says, hey, did we split this already? And if we didn't, then we're not allowed to use this value as the return value. If we did, then we're okay to use this value. That's the tricky part here. All right, the other weird thing with this is we've put these base cases outside of our recursive function. These aren't really base cases, these are more like simple cases that we already know the answer to. So we won't even bother with the recursive function if we get an initial n that's 2 or 3. All right, so if we make it past this initial check of 2 or 3, that means we have to have 4 or greater, which means we can definitely do a split, and it means that we can have our base case of 1 here. We could probably put our base case of 2, but the thing is with 2, we would return 1, but if we've already split once, inside here, we'd still want to return 2. All right, so let's see. I think this is pretty good. I think we could probably remove this now. Let's give this a shot. Do we even need this? So if we remove that, that means we don't have this anymore. So it does mean that our base case will only be reached if we've done one split, because this has to start as 4 or greater. So I think this does work. All right, it works, and it gives us a nice little boost. Now we're at 90% for runtime and 27% for memory, so that's pretty good. All right, so this one is tricky. If you follow the standard recursive function, you can go through, you can reduce the problem by 1 every time you go through the loop. The trickiest part is just realizing that you have to keep track of whether or not you've done a split at all. Now in our initial solution, we were keeping track of this with a Boolean, an explicit Boolean that we passed through. Now in our refinement of the solution, we know that we've done the split already because we didn't get into our recursive function until we've reached at least an n of 4, and because our base case won't return until we reach 1, that means we had to have done at least one split. Okay, I hope this didn't confuse you too much. This is a tricky one. Try it out on your own. Check out some of the solutions here. Actually, we didn't do that. We can look at some of these other solutions, see how other people solve this. They do a similar thing with base case. They actually do an additional base case here, 2 additional base cases. And then, oh, they do some fancy math with this one. So they're actually doing some rounding and some divisions and some multiplications, and wow. This one deserves to be at the top of the list. Much better solution than mine. Okay, well, I'm short on time, so that's it for me. Hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.